G'day and welcome. A lot of my students have difficulty with integrating, and to answer their queries and to try and explain how to integrate, I'm going to create 3 videos. This is the first one, and then a series where I demonstrate the process, but 3, if you like, theory or demonstration videos. And this first one is going to explain the principle, the basic essential principles of integration, and also explain why it is that students get confused. And it's over a very simple little principle. And when you understand what it is, hopefully your confusion will disappear. But the first thing to remember, or to acknowledge, is that integrating is the exact inverse operation to differentiating. It undoes the process. In much the same way that when you have x plus 3 equals 7, and you want to solve for x, to undo the addition of 3, we subtract 3 from both sides. What we call the inverse operation. 3 take away 3 is 0, and we just get x equals 7 take away 3 is 4. So you're familiar with inverse operations. The inverse of x of a power of 2, for example, will be to take the square root. Or if you have a square root, a square will undo that. So inverse operations are designed to do the complete reverse of what some previous operations done to get back to something. I mean, even as children we understand this, and I must have been a strange little kid. I remember as a child being in my backyard and spinning around one direction 10 times to get myself dizzy. Yes, I did count them. 10 times to get myself dizzy, and then spinning myself 10 times the other way to undizzy myself. It never ever worked, but something in my little brain said it should. If I do the exact opposite, it should get back to the way it was before. I had to learn about entropy and things like that as well. So certain processes in the real world don't do that, but in a lot of mathematics we work on inverse functions. And it turns out that when you take a derivative of something, let's say the derivative is x squared, then if you find the integral of both sides with respect to x, that the integral of the derivative of y gives y is the integral of x squared dx. So we differentiate to get one thing and we integrate to work back to the original y value. Having said that, you need to understand that there are 6 functions we need to do this to. Here they are. Y equals x to the power n, y equals sine x, y equals cos x, y equals tan x, y equals e to the x, and y equals log x. These are the standard 6 functions that are generally taught in high schools in Australia, and I suspect pretty much around the world. Now, what are their derivatives? Well, their derivatives are these, and you should become very adept, very practiced at writing these out. And if you don't know them, and if you don't know these patterns really, really well, then my recommendation is that you write them at least once or twice every afternoon. And just after 3 or 4 or 5 days, 2 days, you'll be feeling quite comfortable rattling these off and just doing these in any old order at all. Now, I'm anticipating that if you're watching this video, you've already learned these patterns. That the derivative of the simple logarithm of x, the natural logarithm of x, is 1 over x. The derivative of the exponential is itself. Derivative of tan is sec squared. Derivative of cos is negative sine x. Derivative of sine is cos, and of course the derivative of the power of x is a power 1 less, with the original power as a coefficient out the front. That's the standard set of 6. That's the key to differentiating, and it also becomes our key to integrating. What does it mean? Well, if I do this in reverse, it simply means that if I integrate nx to the n minus 1 dx, if I integrate that with respect to x, I get that. That's not hard. Plus a constant, of course. I'll do that in blue. The same would apply here. The integral of the cosine of x with respect to x is sine x plus a constant. Now I'm not going to do all 6 because that will use up too much time, but I will do the next one. It's rather critical. The integral of negative sine x dx equals the cosine of x plus a constant. I'm not in this video trying to explain all the foundations. I'm assuming you've done this in class, and this is like a revision and a clarification for you. And if I integrate sec squared, I get tan, and if I integrate 1 over x, I get log x plus a constant. If you learn these, if you know those 6 patterns, and if you just memorise that that pattern integrates to that and this integrates to this, you can integrate. Where the confusion appears is this. When we integrate, any constant, any coefficient of a function can move inside or outside the integral sign. In other words, we say it's transparent to it. The way we would express it is that the integral of some number times fx dx is exactly the same as having the number outside the integral of fx dx. Makes no difference. There's a way of proving that, but for the moment we'll just accept that. And I want you to notice that in the case of the cosine, the case of the secant squared, the case of the exponential, the case of 1 over x, there is no constant to worry about. The constant is 1. In other words, this becomes rather irrelevant. But I want you to notice that in this case, and in this case, there is a constant. Here it's negative 1, and here it's n. And the confusion lies because some mathematicians and some teachers and some students prefer a shortcut, what they regard as a shortcut. And the shortcut is this. I'll do it in blue. They say, let's move this negative 1 outside, so it becomes negative the integral of sine x dx is cos x plus c. And let's multiply both sides by negative 1 or divide by negative 1, and we get the integral of sine x dx is negative cos x minus c. Well, I'm just going to call it some other constant, just so it looks simpler. And they memorise this. Now, all that's really happened is this negative sign's moved across in front of the cosine, as you can see. But they prefer memorising this. I say they, I use both, so it really doesn't bother me. I've practiced a lot. But you can understand that some students will get confused between the two. What do you do with the sign, the negative sign? This one here, they did the same thing. Move the n outside the integral. And then divide both sides by n. And this side would simply be x to the power n minus 1 dx equals x to the n over n plus c over n. Well, I'll just give it a different constant just to make that look simpler. And they memorise this rather than that. This is where the confusion is. Which one should you use? Well, it really doesn't matter. And I'll demonstrate using this one. Actually, I'll do it in blue over here. Let's imagine that I'm integrating 5x to the 7 dx. Let's imagine I've got that. Now this does not conform to the standard basic pattern. If I had a power of 7 here, that's one less than this, so this would be an 8. And I certainly don't have an 8 there. Now, both methods would move the 5 outside, so I'm going to write this, x to the 7 dx, and I'm going to write it again. And in black, I'm going to show you the difference. The top method, the first method, would say we want to see this pattern with the n inside. And remember, we expected to have an 8 here. We would like to see the integral of 8x to the power 7 dx. Now if we introduce an 8 here, we have to divide by 8 on the outside, remembering that this is multiplied, and 1/8 of 8, or 5/8 of 8 is 5, or the 8's divide out, however you wish to think of it. And the integral in this case would be 5/8 outside, and the integral following this pattern of 8x to the 7 dx would simply be x to the power 8 plus a constant. If we did it the bottom way, we simply leave the 5, and the integral of x to the 7 is x to the 8 over 8. Plus c. Now, both these expressions have exactly the same meaning. It doesn't matter when you're multiplying these, whether the 8 is under the 5 or under the 8, x to the power 8, or indeed under both, they all mean the same thing. So there's absolutely no difference in the answer. There's just this little difference in how you approach it, and it's a personal preference. Let no one tell you must do it this way or you must do it that way. My preference, psychologically, is to do it this way. And you will see later in the next video, on the third one, that it simplifies matters considerably if you think of the pattern as a pure pattern of reversing the derivative. So there's a certain attractiveness about this, but I must admit, in the case of powers of x, I use this frequently, simply because it's fast and it's something I've adopted, and I've overcome the problem of confusion. So if I'm integrating x cubed minus 7x dx, I would simply write x to the power 4 on 4. That's following this pattern where you just add 1 to the index and then write the number on the bottom. Minus 7, that's like the number that's sitting out the front. Now the integral of x to the power 1 will be x to the power 2 on 2 plus a constant. And I find that quite an attractive way of integrating. But if a student preferred, they could write this as the integral of x cubed minus 7 times the integral of x, both with respect to x. And to follow the pattern, they would need a 4 here, one more than the 3. And they would need a 2 here, and adjust out front. And you can see this is a bit more fiddly. And that would also give us 1/4 x to the 4, there it is, and 7 over 2 x squared. You can see why I prefer the shorter version in that case. But in virtually every other case, I stay with the exact form. And I'll be demonstrating that, as I say, in the future. I hope, if you've been having trouble, I hope that's helped explain the confusion between the two methods. I'd encourage you to practice both. Perhaps just for a remaining 2 minutes, I might just wipe this and put a quick example on the board, just to really drive home the difference. But my main objective here was for you to see the 6 patterns, to see the pure inverse function backwards in terms of integration, and to understand why the confusion and to overcome it. Let me do 2 quick examples perhaps, or 1 quick example, and then we'll call it quits. Well, I couldn't help myself. These are going to be 4 quick ones. I'm going to do this the short, quick way, and the others the more formal way. The short, quick way here would be to write 3, integrating x squared would be x cubed on 3, minus 5, integrating x to the power 1 will be x squared on 2, plus 8. Now, technically, there's an x to the 0 here, and integrating that would be giving me x to the 1 on 1. And that would, of course, 3's would divide out, it would be x cubed, minus 5x squared on 2, plus 8x plus c. That one's finished. It's quite a nice method, and I recommend it to you, and I really recommend that you practice till you're fast. You'll know in your heart of hearts when you're right. Now this one here, I know this. I know that the integral of negative sine x dx is cosine of x. That's what I would love to integrate. And because of that, I'm going to move the 6 outside. So it's moved outside. And because I'm going to put a minus sign in here, I'm going to put, or a negative sign, I'm going to put a negative sign there. Because they're multiplied, and a negative times a negative would give me a positive. And now I just leave the negative 6, and the integral of this is cosine of x, plus a constant, of course. This is a rather sweet way of doing it. This one here, if I move the 8 outside, the integral of sec squared dx, that's one of our pure integrals, is exactly tan x. And this one here, if I'm, actually you notice I've got a 5 and a 3 that are in the road, so I'll move both of them out. 5 on 3 times 1 on x dx. This is sometimes written as dx over x. Means the same thing. And this pattern, integrating 1 on x, this is the pure pattern for the logarithm. Remember the derivative of log x was 1 on x. So my answer is 5 on 3 times, and the integral of this is log x. And that's it. Just get to recognise those key 6 patterns, and they'll stand you in good stead. And remember that you can do what you like with the numbers, the coefficients at the front. Next video, I encourage you to watch out for. We're going to see how, when we don't have a pure function, when we have a function of a function, or a chain rule if you like, how that works. So we're going to be integrating the anti-chain rule if you like. I thank you for watching and encourage you to leave your comments, to like the video and to subscribe. Thank you.